Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic mechanical engineering. We'll dive into key concepts like thermodynamic system, properties, state, process. Slide 1. Introduction to thermodynamic system. Let us begin by understanding what a thermodynamic system is. A thermodynamic system is a specific part of the universe we choose to study, such as gas inside a cylinder. Everything outside the system is called the surroundings. The boundary is the surface that separates the system and its surroundings. This boundary can be fixed or movable, real or imaginary. There are three types of systems. 1. Open system. Both mass and energy, heat or work, can cross the boundary. Example: a steam turbine. 2. Closed system. Only energy can cross the boundary, but mass cannot. Example: gas in a piston cylinder if sealed. 3. Isolated system. Neither mass nor energy can cross the boundary. Example: a perfectly insulated thermos. We also use the concept of control volume, which is a region in space where mass and energy enter and exit, commonly used in flow systems. Understanding these systems helps us model real-world machines like engines, refrigerators, or compressors. Slide 2. Thermodynamic properties. Thermodynamic properties describe the condition of a system. These are measurable quantities that help define the system's state. We divide properties into two main categories. Intensive properties. These do not depend on the system's size or mass. Examples include pressure, temperature, and density. Extensive properties. These depend on the size or mass of the system. Examples include volume, energy, and mass. When we divide extensive properties by mass, we get specific properties, such as specific volume or specific enthalpy. Another important classification is state functions, point functions. Their values depend only on the initial and final states, not on how the process occurs, e.g., internal energy. Path functions. Their values depend on the path taken, e.g., work, heat. Recognizing which property is which helps us apply thermodynamic equations correctly. Slide 3. Thermodynamic state. The state of a system is defined by its properties at a given moment, such as pressure, temperature, and volume. When all parts of the system are in equilibrium, thermal, mechanical, and chemical, the system is in a state of equilibrium. A state point is simply a point on a graph or diagram that represents a unique state of the system. When we connect different states on such a diagram, we see a process. A quasi-static process is a slow process that allows the system to be in near equilibrium throughout. This type of process is idealized but helps us apply thermodynamic formulas easily. For example, a gas slowly compressed in a cylinder follows a quasi-static process and has clearly defined intermediate states. The importance of defining a state is that once we know the state, we can calculate other properties like energy, work done, or heat transfer. Slide 4. Thermodynamic process types. When a system changes from one state to another, the path it takes is called a process. Let's look at the common types of thermodynamic processes. 1. Isothermal. Temperature remains constant. The gas cools or heats to maintain the temperature during compression or expansion. 2. Adiabatic. No heat is exchanged with surroundings. Rapid compression of air in a pump is adiabatic. 3. Isochoric. Isovolumetric. Volume remains constant. Heating gas in a sealed container is an example. 4. Isobaric. Pressure remains constant. Boiling water at atmospheric pressure is isobaric. 5. Reversible process. Ideal, very slow, and can be reversed without losses. 6. Irreversible process. Real processes with losses due to friction, heat loss, etc. 7. Polytropic process. follows the equation PV to the power of n equals constant, where n is the polytropic index. Different values of n represent different processes. Each process affects the energy interactions differently, which is why classification helps in thermodynamic analysis. Slide 5. Differences, open, closed, and isolated systems. This table compares the three types of systems based on key features. In summary, open systems are widely used and involve both heat and mass flow. Closed systems are common in ideal cycle analysis. Isolated systems are mostly theoretical models used to simplify complex problems. Understanding these differences helps students select appropriate systems for engineering problem solving. Slide 6. Significance of studying thermodynamic terms. Now that we've covered systems, properties, state, and processes, it's essential to understand why these terms matter. 1. They help us analyze how energy is transferred and transformed in machines like engines or refrigerators. 2. They form the foundation for designing efficient machines. 3. Identifying the correct type of system helps us apply the first and second laws of thermodynamics correctly. 4. Understanding properties enables us to predict system behavior under varying conditions. 5. Knowing the state of the system allows for calculations like heat input, work output, etc. 6. Classifying the process, isothermal, adiabatic, etc., helps in energy balance equations. 7. In industries like power plants, aerospace, HVAC, and automotive, thermodynamic understanding is essential. 8. For example, a refrigerator uses a closed system and undergoes cyclic processes involving all types of energy transfers. 9. In summary, thermodynamic terminology isn't just theory, it's a toolbox used by engineers daily.